All right. Look, the problem is super straightforward. So, and we've done it. So I don't want to spend a lot of time here because there's not really a whole lot to do. You're supposed to find out how fast it's going at the bottom of a ramp. So that's what question number 5 is about. You could find linear speed or angular speed. I don't really care, but I think linear speed is probably what to go for here. So the important detail, I think, is we're told the height of the ramp, or we told the length of the ramp and the angle. I don't remember. We're told the length of the ramp and the angle. Okay. So we'll go with theta and the length of the ramp. Something like that. Is that good for you guys? I don't care what the object is. They tell us it's a disk. We could leave it in terms of I if you'd like. And that way we can plug in any shape. How would you like this to be performed? With the disk. So you need to know things about the disk then. And the most important thing they tell you is that it's a disk of mass m and radius r. If you do it in terms of I, you could just plug in I at the very end. But if we have the value of I, we can plug it in now. I want to let you to sink in the idea that if you put in I here and leave I in the equation the whole time, at the very end you have the answer for every single thing you could possibly put in there. But we'll put it in for the disk. There's 2 ways to do this, as we discussed yesterday. You could find the acceleration of the disk using forces, and then use a motion equation to find out how fast it's going at the bottom. I think that's the harder way to do it. As we discussed yesterday, it's not about whether it's easy or hard. You're just employing the rules. But from my vantage point, looking at these questions, I think it's a more difficult question to use forces than energy. Most of the time, energy is faster and more efficient. And also, energy would answer questions that forces couldn't answer. Like if this weren't a straight path, but maybe a ramp that was curved like that, we wouldn't be able to use forces because the forces would be different the whole time. As you are trying to delineate what to use, this is me filling in more information about how to solve problems. So I want to, going back here, there's a clear change in height. That's why energy seems like a pretty good place to start. But in order to understand that, we need to know what the change in height is going to be. And for that, we'll probably need some trig. Yeah. Okay. I think that's how we'll get the height, right? It's a triangle. You'll need to be able to do that without difficulty. At the very top, it's going to have gravitational potential energy. Very bottom, it's going to have 2 forms of energy, assuming it's rolling. And I think we're indicating that it is rolling. So mgh is going to equal 1/2 mv squared plus 1/2 I omega squared. Now here's where you could leave I in the problem and just work the whole problem all the way through, leaving I in there, and then you can put the shape in at the last minute. You said you didn't want to do it that way, so we're going to put in the shape now. But you have to do more than just put it in the shape. You also have to decide, do you want your answer in terms of the angular speed, or do you want your answer in terms of the linear speed? Since nobody's writing their pencil or wiggling it, that's something that you should write down. Pay attention. You either put everything in terms of the angular speed or everything in terms of the linear speed. One answer depends on the shape. One answer doesn't. That's why I think it'd be important to note the difference. So we are going to note the difference. We're going to do one version and find angular speed. And one version and find linear speed. Okay. On the linear speed side, we're going to have mgh equals 1/2 mv squared plus 1/2 I, and we will replace omega with v over r squared. this gives us the linear speed. On this side, though, mgh equals 1/2 m, not v, but omega times r squared, plus 1/2 I omega squared. I think it's important that you see something here, which is worth doing two different ways. We have an expression for I. We said it's a disk, but remember, I determines how difficult the object is to turn. You know this is the AP1 exam. You will have to explain yourself. A disk takes more energy to get spinning than, say, a solid sphere. But it takes less energy to get spinning than a ring. I gave you all those moments of inertia. I'll even give you the table too, but you have to be able to recognize that disks, rings, solid spheres, hollow spheres, they all roll different because of the way their mass is distributed. That's the thing about I. Leaving it in the problem means you can plug it in at the end and make comparisons. Putting it in now means you might have to do the problem more than once if you need to make a mathematical comparison between the two. So be ready to be able to give a reasonable discussion. So at the end of this, you should be able to tell me that if we put a ring there, would it be going faster or slower at the bottom? You can either do the math again, or you can make a reasonable argument. I don't know if you can make a reasonable argument, which is why putting the ring in there and working out the math might be useful to you. I'm going to go ahead and put L sine theta, because we're going to have that in there eventually. I is 1/2 mr squared. This side. All good? Algebra, you guys are pretty good at it, but you make mistakes. I hope you don't make a mistake here. We've done this one already. The R's cancel out. The M's cancel out. The 4/3. That's a product of the inertia. That number would be different if the object were a different shape. That's a number that would change. So if it were a ring, you get a different number there. If it were a solid sphere, you get a different number there. But the reason why you should do question 6 before you do question 5 is because this tells me that the linear velocity at the bottom won't matter whether it's a big disk or a small disk. The mass canceled out and the radius canceled out. So whether it's the CD rolling down the ramp or the record rolling down the ramp, the only thing that will determine its speed is the length of the ramp, the angle, and G. So if you do 6 first, the answer must be the same for the vinyl record or the CD. You see why I would do a 6 first? So if you did 5 first, okay, you should have gotten the same answer for both of them. If you didn't, you probably made a mistake. Let's do the other side though. A lot of this is the same. I can cancel out the M. Can't cancel out the R. But I can solve this for omega. Oh, wait. I was jumping ahead. It's 3/4 here. Just getting ahead of myself. Don't curse me. Now, angular speed, linear speed. I don't know if you know why this makes sense or doesn't make sense, but you should. They both have the same linear speed. In order for two things to have the same linear speed, the smaller one will probably have to be spinning faster than the bigger one if they're traveling at the same speed. I think that's something you should be able to put into words. This is put into math speak. But can you see that because the r is in the denominator, that if you make r bigger, the angular speed will be smaller? I think you should see that. In fact, if you are really paying attention, you'll understand that all you had to do was take this and divide by r, and you would have gotten the angular speed, because v equals omega times r. That's what this looks like over here. Just pull the r out. And it's the same thing. So I think it's important that you know that although they both have the same linear speed, one is spinning faster than the other. Which one? The CD or the vinyl record? Which one is spinning faster at the bottom?
CD.
Why?
Its radius is smaller.
Its radius is smaller. Yeah, that's it. All of those things, if you couldn't say that just now, how many points do you think you'll earn on your next test? So take a minute and write that kind of stuff in. Give yourself the information you need here. Why is one of these numbers different? And what would be different if something had a smaller radius or a bigger radius? I mean, this is the problem. This is the kind of thing I'm giving you ahead of time. I'm telling you the test questions and the kinds of things you'll be asked to explain. So take a minute. So if you have three things and you know their moments of inertia and they have the same shared axis of rotation, then you can just add up all three moments of inertia. And since they're all the same, it's just going to be 3 times the moment of inertia. So 3 times 1/12 ml squared is the moment of inertia of this system, which is 1/4 ml squared. Set that aside. How much energy is required to spin up the blades from rest? Well, from rest, that would be the change in kinetic energy. And it's just rotational kinetic energy because it's not talking about them going anywhere, just spinning. So 1/2 I omega final squared minus 1/2 I omega naught squared. I like how you guys feverishly are writing these down because you definitely didn't do this homework question, so you want to make sure you get this one in there. When I look at your homework and I see it all out of order, I can tell that you're just doing the ones we did in class, and then whatever's left over you'll do at the end. Procrastinator's dream. Is that enough information to tell you what to do?
Well, what do you do with this 200 to the 600 RPM?
Well, the way the question is worded, can you say it one more time so I make sure I get it right?
It's what is the energy required to get it up to its range of spinning speeds between 200 RPM and 600 RPM?
Well, I think you'd find out how much energy it takes to get it up to 200 RPM, and then do the problem again to find out how much energy it takes to get it up to 600 RPM. It's saying what is the energy required to get it up to the range. So it's going to take between the up to 200 and up to 600. That's how much energy it would take. Does that make sense?
Yes.
Be careful though. Rotational speeds in this calculation have to be in radians per second. And the rotational speeds there are given in RPMs. So you'll have to convert those to radians per second before you can use them here.
Thank you.
You're welcome. So question 1, the thing is spinning. I want you to find a relationship between omega and theta. L, is this L? Is that what they tell us to use?
Yes.
L and M can be in your answers, if necessary, and probably G and stuff like that.
Universal constants.
I would do this as forces and remember what UCM stands for. Do you? Uniform circular motion. They're in uniform circular motion. There is a two forces acting in a system and one is unbalanced. You can do this. I believe in you. You'll know you've got it done right if there's a tangent in your answer. Continually go back to something, and I think you should be having a section of your notes that you just call problem-solving skill. And I would arrange it like this, with this first column being forces, Newton's laws, and this being work and energy, and this one being momentum, impulse. I'm trying to organize your problem-solving skill page, and I'm trying to help you. I did more of this differently in second period, and I think we started something like this in this class. So as we fill these things in and try and flesh them out, oftentimes you can use forces with motion equations. Can't fit in the word displacement, so I'll just put in delta x. Newton's laws are really good at telling you a force or an acceleration, but they could be used to get speed or displacement. But that's only if the forces are constant. If the forces aren't constant, then you can't use a motion equation. The only motion equation we know, the ones that we derived, are for constant accelerations. Work and energy, great for getting you displacements, and speeds. They're great for that. However, doesn't tell you direction. Never does, because energy doesn't have direction. You can infer it sometimes, but it doesn't tell you direction. That's why with the v being squared all the time, remember, every time you take the square root, you have to decide whether that root is positive or negative to help you determine direction. Now, at the same time, you can get acceleration. You'd have to use a motion equation. Again, if the accel is constant. So in this case, this problem can be done both sides, no troubles, just pick one. But a ramp like this, the acceleration is not constant. So you couldn't use forces on this easily to find velocity or anything like that. Just trying to give you things to look for. So we were working the math part of that yesterday. We didn't finish, we got close, if you'll recall. We were working out the forces, and we drew the forces on it. So it doesn't say whether it's rolling up the ramp or down the ramp, but it doesn't matter. So let's take a look at the basics of that question for just a quick minute. It says a ring and a solid sphere, is that right? Or hollow sphere and a solid sphere? All right, just to differentiate, I'm going to draw the hollow sphere like a ring and the solid sphere filled in. And which one is going to experience more friction. To do this problem without using any math, I want to first bring up, and this is not about math, it's about being able to tell which one of these is more difficult to turn and which one is easier to turn. So we have the moment of inertia of a solid sphere versus a hollow sphere. All things that are circular have mr squared as part of their moment of inertia. So it's going to be something mr squared. A solid sphere has more mass near its center than a hollow sphere does. You want an explanation, right? How do you describe that? How would we look at the difference without using math? Well, a hollow sphere is empty on the inside. So most all of its mass is all on the outside. But a solid sphere, solid all the way through. Much more of its mass is towards the center of a solid sphere. That's the kind of thing you probably would have to write down. That's going to make the moment of inertia of a solid sphere less than the moment of inertia of a hollow sphere. But it's also on the board, right in front of you, right now. Those are the two. A hollow sphere is 2/3, and a solid sphere is 2/5 mr squared. What number's bigger, 2/3 or 2/5? 2/3 is bigger than 2/5. Great. So we have a clear understanding that the hollow sphere is more difficult to turn than the solid sphere. There are 3 forces acting on the object. Normal force. Does it cause the object to turn? Now, you should be able to explain why or if each of these forces causes it to turn. The normal force doesn't cause it to turn because the force is pointed towards the center, so it can't cause it to turn. There's weight and there's friction. You need to identify where your axis of rotation is going to be. Do you think this object spins about this point or this point? It makes no difference. You need to pick one of these. So raise your hand if you think it's this, you want to do it through the center. That's the majority of the class. So we're going to consider that the axis of rotation is through the center. That's good because these moments of inertia are based on through the center. Of these 3 forces, which one is responsible for turning the object? David? Friction. Friction is the only one of these 3 that has a torque arm that can apply a torque. The torque arm is the distance from the axis of rotation. Ooh, that's a bad choice. Is the distance from the axis of rotation to the place where the force is applied. So that's this. That's the torque arm. We're not allowed to use math here. I'm just providing you with reasons why the frictional force is causing a torque and the weight isn't. The weight is acting at the center. There's no torque arm. That's not a torque. The friction is acting at the edge. There's a torque arm there. That's causing it to turn. Now, that's really all the setup that I need. It is the friction that's causing it to turn. Which one is harder to turn? The hollow sphere or the solid sphere? The hollow sphere. Right. So the one that's going to be harder to turn is going to probably require more friction to get it to turn. And you might say, well, what do you mean more friction? Well, friction in this case is static friction and is an inequality. A surface can provide as much friction as necessary up to a limit. This represents the limit, but a hollow sphere might not take as much of that friction as a solid sphere. A solid sphere might not take as much of the friction as a hollow sphere would. The hollow sphere is harder to turn. The things I think have to be in your expression when you talk about it. You have to explain how the frictional force is connected to the problem. That's what we did here by determining that the friction is causing the torque on the object. Then we have to say something about how torque and moment of inertia are related. Now, there's more to this question, and we didn't get a chance to get all of it explored, but we got a pretty long way.